Up in third are our venomous lizards, such as the beaded lizard. We're obtaining venom from here using our specialized, highly innovative technique based upon leading-edge equipment.
So what we're going to do is milk this beaded. Come on, darling. Pop your mouth open. The easiest way to milk them is have them bite down on something, and then as they start chewing, they'll secrete out the venom, and it absolutely just starts flowing. Alright, so he's biting now, so that's good. The way they deliver their venom is that they bite and they hang on and sit there and chew and chew and chew and chew. Sometimes they'll even flip onto their back while they're chewing, but they don't let go. They're like little bulldogs. So it's a very different attack strategy than a Komodo dragon. You can see all the drops of venom on the parafilm. It's actually quite a good little yield of this one.
However, there's a lot more venomous lizards out there than have been historically thought. For the longest time, only the helodermatid lizards, beaded lizards, and Gila monsters were thought to be venomous. However, our research has shown there's a lot more venomous lizards out there, a few hundred in fact. All of these are located within a group of related lizards called the Anguiomorpha lizards, which includes the Gila monster and the iconic Komodo dragon. This also includes the extinct giant Megalania, a relative of the Komodo dragon in Australia that reached an estimated 7 meters in length, which would make it the largest venomous animal to have ever lived. Now, venom in lizards evolved from the same ancestral starting substrate as snakes. The last common ancestor of the reptile clade Toxicofera was unique in having protein-secreting glands on the upper and lower jaws. This doesn't mean that the last common ancestor was venomous per se, that evolution doesn't sort of go in a quantum binary leap. Rather, there's a squishy, controversial middle. But rather, that this is where the reptile venom singularity occurred. From there, lizards and snakes took totally different evolutionary paths, with lizards developing the glands on each side of the lower jaw into proper venom glands, while snakes did the reverse, developing the glands on each side of the upper jaw into proper venom glands. In Anguiomorpha lizards, the basal condition is a gland that's made up by multiple small compartments, one per tooth, so about 16 on a side, 32 in total. This form is retained in alligator lizards from the Americas, but then it got a bit more interesting. On 2 independent occasions, a bunch of these little compartments were fused together to make several big compartments. And this was paralleled by the gland becoming bigger yet again in each of these convergent cases. This was accompanied by a hollowing out of the gland to form a venom storage structure called a lumen, with this supergland now able to make and store more venom. So this happened once in the last common ancestor of the helodermatid lizards, your beaded lizards and Gila monster, and then happened independently in the last common ancestor of your varanoid lizards, which are your Borneo earless monitor and your monitor lizards. Now, what's really interesting is that in both cases, they convergently ended up with the same number of big compartments, 6. In each case, there's a large circular lumen in each of the remaining compartments, able to store appreciable amounts of venom, such as over 200 milligrams in the case of a Komodo dragon. Now, paralleling the changes in the venom gland were changes in the venom. The ancestral version of Anguiomorph lizard venom is to be rich in a type of serine protease enzyme called acalocrene, which is a trait shared with snakes, reflective of the common history of the glands. Now, these enzymes are multifunctional. They're able to exert diverse toxic effects, such as the destruction of the essential blood clot component fibrinogen, creating an anticoagulant state, through to being able to drop blood pressure like a stone by cleaving a component called kininogen and release potent hypotensive peptides called bradykinins. However, the venom within the monitor lizards is evolving at a particularly fast rate, with the venom between different species of monitors as different from each other as would be the case between equally related snakes, showing that monitor lizard venom is actively evolving under a positive selection pressure. But if we step back a little bit further into the last common ancestor of our helodermatids and our varanids, that in our basal venom, we have the emergence of powerful neurotoxins. We've recently published on these. If you go to my webpage, venomdoc.com, select the lab publications section from the drop-down menu, all of our papers are in there. It's beyond the scope of this segment to go into full detail of the evolution of the lizard venom system, but I'll be doing a future episode just on lizard venom, so please stay tuned for that if it's something that interests you. Now, to round up this episode, we'll conclude with stating that based on the current research, the most toxic lizards are the helodermatids. Now, beaded lizards have a larger venom yield, and it appears that Gila monsters in some assays are a bit more toxic, therefore offsetting it, so we would rate them as equally dangerous. Human deaths have occurred, but they are few and far between because these are very rare lizards and therefore bites don't happen very often, and often they're just short contact bites, not a long, prolonged chew. And they don't deliver the venom as quickly as a snake, which has hollow syringe-like fangs. There is, however, no antivenom. But like many other venomous animals, they've been a source of new therapeutic drugs. In the case of the helodermatids, the development of a blockbuster treatment for diabetes using a component called beta. Now, this reinforces that we need to conserve all of nature because we can't predict where the next wonder drug is going to come from. So here we have a diabetes treatment from a critically endangered group of lizards, underscoring that if we lose these kinds of animals, we lose future life-saving and money-making drugs.